Hello everyone. Title of this video is Section 7.5 Part 2 on uniform motion, work, and problem solving. So in this video I'm going to be going over a version of the Newton Alta assignment for Section 7.5 Part 2. Please understand that the version I work on in this video, the questions you see, may or may not be exactly the same questions you will see when you work on the assignment on your own. But the objectives will be the same, the types of questions will be similar, and how you would go about working on them would also be very similar to what I'm going to do. So I'm hoping that watching me do this here helps you when you work on the assignment on your own. All right. And I would also request that whenever a new question pops up, pause the video and try to work on it on your own. Try to finish it on your own first, and then watch me do it and see how you did. Right? Because if you're just watching me do it without practicing on your own, you're probably not going to learn all that much. Alright, so here's your assignment page. You got, you won't see the words preview of, you'll just have the title of the assignment, the mastery bar telling you how far along you've gotten, the objectives. Looks like there are 2 objectives in this assignment. And at the bottom of every question there should be a feedback button to send feedback to Newton, and a more instruction button. Right, you won't see the instructor sheet button. Right. You'll have a more instruction button that if you click on, you'll be provided with extra reading material or videos for whatever particular objective you're working on, and hopefully those help you. Alright, so this first question is on the objective, use rational equations to solve uniform motion problems, uniform motion applications. So every single question in this is going to be some sort of word problem, and it's our job to set up an equation. And in this particular section we're going to be setting up rational equations, right? Equations involving fractions. And then solving those equations and using those solutions to answer whatever question we're being asked. Alright, so I'll read this question. The first step is obviously to read through the question in its entirety, right? And hopefully you understand what's being asked for. So here we have Dana enjoys taking her dog for a walk, but sometimes her dog gets away and she has to run after him. Dana walked her dog for 7 miles, but then had to run for 1 mile, spending a total time of 2.5 hours with her dog. Her running speed was 3 miles per hour faster than her walking speed. Find her walking speed. Okay. So I've read through this. Now I'm going to pull up a piece of paper here along with the problem. I know the problem just got a little tinier, but and I'm going to write out the information that we have. All right. Now all of these uniform motion problems, right, uniform motion, and I'll make this page bigger, the paper I'm writing on, after I'm done writing out the information I want. All these uniform motion problems, you're going to be using the following equation. Right. The distance traveled, will be equal to the rate of travel. Now, rate of travel could also be called speed. It's how fast you travel for, multiplied by, right, little time symbol there, the time traveled for. All right, now that's a very long way of saying this. Very often you'll see it written this way. D equals R times T. All right. Distance equals rate times time. For example, now when they say uniform motion, that just means you're moving at the same speed all the time, the same rate. So for instance, if I was traveling 50 miles an hour, that'd be the rate, 50 miles per hour, or rate per, 50 miles per hour times 2 hours, right? If I was going 50 miles an hour for 2 hours, 50 times 2 is 100, that'd be 100 miles. 100 miles traveled. So every single uniform motion problem will involve this formula in some way, and you're going to have to know this, right? That distance equals rate or speed times time. All right. Now, very often in the uniform motion problems, I would recommend making a little table, a distance, rate, and time table. All right, so here's a table. And we're going to have a distance, rate, right, or speed, and time columns. And for most of these problems, there will be 2 rows, right? Talking about two different types of motion, 2 different types of traveling. We had walking, right? Dana walking, that was one type of travel. And we had Dana running, right? The other kind of travel, the other type of movement, the other type of motion. And let's read through it again. Alright, so the first sentence is meaningless. I mean, it's not meaningless. It talks about her walking and running, but it's like it has no numbers. It has no value to us, right? Dana enjoys taking her dog for a walk, but sometimes her dog gets away and she has to run after him. Okay. Dana walked her dog for 7 miles. That is a distance, right? The distances here look like they're going to be in miles, right? So the distances will be in miles. I'm putting the units up here. The time, they mentioned 2.5 hours, so time's going to be in hours. And if the distance is in miles and the time is in hours, then the speed will be in miles per hour, right? Miles divided by hours, right? And that's where our fractions are coming in here, right? Oh, you'll see the fractions coming later, right? So again, I would recommend setting up a little table like this with the 2 rows for the 2 different kinds of travel. Alright, so Dana walked her dog for 7 miles. So that's the distance in the walking row. Alright, so I'm just putting 7 there. But then had to run for 1 mile. So the running distance was 1 mile. She spent a total time of 2.5 hours with her dog. Alright, you know what? We'll talk about time here in a second. That's where the fraction's going to come in. I'll show you what I mean. Her running speed was 3 miles an hour faster than her walking speed. Find her walking speed. Let's say that Dana's walking speed, right? It's just like any word problem. You read through it. What are they asking me for, right? They're asking me for Dana's walking speed. I'm going to call this W or X or whatever you want, right? You read through it, you find out what they want to know, what are they asking me for, what's unknown, and you call it something. W. So that's the walking speed. W miles per hour. Again, this is miles per hour. I put W there. And then it said her running speed was 3 miles per hour faster than her walking speed. So the running speed under rate here is the walking speed plus 3. Right? W miles per hour walking, and then 3 miles an hour faster. Right? I hope that makes sense. So I'm putting W plus 3 here. Now in the time area is where we're going to get our fractions. Let me show you. Because if distance equals rate times time, then the time is distance divided by rate. Right? If the distance traveled is the rate times the time, then the time is the distance by the rate, and that's how I'm going to fill in these parts of these tables. So let me make this a little bigger now. All right. Here we go. So time is distance divided by rate. So the time traveled walking would be the 7 miles divided by the W miles per hour that she walked for. And the time traveled running would be the 1 mile divided by the W plus 3 miles per hour speed. So here are the fractions. Now comes the equation, right? And that one sentence says her total time, right? Dana's total time traveled was 2.5 hours, right? Is 2.5 hours. Or I'm going to write 5 halves just to make more fractions. Right? 2.5 is the same thing as 5 halves. Total time. So adding these times together would give me 2.5 hours. And here comes the equation. So the time walking, which is 7 divided by W hours, plus the time running, right, which is 1 over W plus 3 hours, right, this is the number of hours here, should be equal, right, this is the total time on the left side, and then the 2.5 hours on the right, 5 halves. So we're solving this equation. And that's the hardest part. I think the hardest part is setting up the equation, not solving it, but actually setting it up, reading through a word problem and actually figuring out how to set up an equation. But once the equation is set up, the rest should be pretty simple. You know, it's a rational equation, right? An equation with fractions. So remember how to do that. First we find the LCD, which is, all these denominators are already factored. The LCD is just the product of 2 times W times the quantity, W plus 3, this other denominator here. And then I multiply both sides, right, every single term by the LCD. So I'm just going to write it this way. So we're multiplying that 7 over W by the LCD, plus, we're multiplying the 1 over W plus 3 by the LCD. So the left side is multiplied by the LCD. And we're also multiplying the right side by the LCD, right? So I'm multiplying all these things by the LCD. And the reason for doing that is so that all the denominators go away, right? All the denominators will cancel. So the first fraction on the left side, the 7 over W, when I multiply by the LCD, the W's would cancel. And I'd be left with 7 times 2 times W plus 3, or 14 times the quantity W plus 3. Right, that's what I'm left over with after I multiply the first fraction by the LCD. Right, plus multiplying the second fraction by the LCD, the W plus 3's would cancel. And I'm left with 1 times 2 times W, which is just 2W. Right, and equals. Then on the other side, multiplying the 5 halves, the 2.5 hours by this, the 2's would cancel. And I'd be left with 5 times W plus 3. Right. And now we have an equation with no fractions, right? A polynomial equation, which you should be able to solve. Right? Now remember, this is going to be a quadratic because you'll have a W squared, and hopefully you remember how to solve by factoring. I'm not going to get into all that, right? So I would distribute the 14. Left side we'd have 16W total, 14W plus 2W, and then 3 times 14 is 42, right, plus 42, 30 plus 12, equals, and then over here I'm distributing 5W, that gives me 5W squared plus 15W, And then if I were to take everything to the right side and then I'll switch sides, we'd have 5w squared. And then the 15w minus 16w would be minus w. And I would subtract 42, and minus 42 equals 0. Right? Then we try, factoring this, if possible. And I'll think about that. Right? Now let's do try the AC method. Let's see, 5 times negative 42, that'd be negative 210. And what I'm looking for is a pair of factors of negative 210 that would add up to negative 1. Now I'll think about that and come back when I have these factored here. Alright, so I thought about it a little bit. Now one factor has to have 5w, the other factor has to have w. And I already know that 3 and 14 go into 42. So if I did this, if I put minus 3 here and plus 14 here, we'd have our minus 15w plus 14w making the minus 1w, and there we go. Then by that zero product property, or the only way a product is equal to 0 is if if one of the factors is 0. 5w plus 14 would be equal to 0 if w were equal to negative 14 fifths. And w minus 3 would be equal to 0 if w were equal to 3. Now, think about it. Think about what makes sense in the problem. Because remember what w represented. W represented Dana's walking speed in miles per hour. So does it make sense to say that she walked negative 14 fifths or negative 2.8 miles per hour? Speed is never negative. Velocity can be negative, right, if we were talking about velocity, but we're not getting into all that. So this doesn't make sense, her to be walking negative 14 fifths miles per hour. This other one does, though. If she were walking 3 miles an hour, that would make perfect sense. And yeah, let's see, right? Let's see if this makes sense back in our little table here, or back in the description of the problem, right? If she were walking 3 miles an hour for 7/3 hours or 2 1/3 hours, that would be 7 miles. Beautiful. If she were walking, and if she were walking 3 miles an hour, that means she'd be running 6, right? W plus 3. And if she were running 6 miles an hour for 1/6 of an hour, that's a mile. So this one actually makes sense. The other value does work, right? Negative 14 fifths would work for W. It's just, it doesn't make sense as a speed. Right? That's why I crossed it out. So again, think about what actually makes sense back in the problem. And again, that's what they called it S instead of W. My bad. All right. So they called her walking speed S for speed, I think. I called it W for W, but either way, it ends up being 3 mph, right? 3 miles per hour. And submit. And wonderful. Now, after every question, whether you're right or wrong, you'll be given an answer explanation. Now, they don't make a table like I did. They explain everything in sentences, but please read through the answer explanations, whether you're right or wrong. If you're correct, just glance through it and make sure you were right for the right reasons, and that you didn't just get lucky. If you were incorrect, definitely read through it. Try to figure out why you were wrong, what went wrong, and try to learn from your mistakes for future questions. Also, if you're right and you read through it, maybe they'll go through an alternate method that you didn't think about that you might want to try in the future. So either way, please read through the answer explanations. All right, next question. All right, so this is on the other applications, work, right? Use rational equations to solve problems involving rates of work. And you're going to see this is very similar to the uniform motion questions, right? And like I said, I'll bring this up and I'll make a very similar table and everything, right? So we have here Lisa takes 3 hours to mow the lawn, while her cousin Barb takes 2 hours. How long would it take them working together? Right, how long would it take them working together? All right, so let's figure that out. Right, I'll bring this up on the page here. I got a new piece of paper. Again, I'll keep the problem up here, and then once I'm done writing out all the pertinent information, I'll bring the page up a little bigger. All right, so now these work problems, right? Doing a job. You know, here it's mowing the lawn. We're going to do the same deal, right? The amount of work, it's a very similar formula. The amount of work done is equal to the rate of work, right? How fast you're working, you know, per hour or per day or per minute. It's like miles per hour, but you know, work per hour, work per minute, work per day. You know, the rate of work multiplied by the amount of time worked. All right. So in other words, we put, you know, W for work. All right, W for work equals rate, the rate at which you work times time. So see, it's a very, very similar formula that's coming up for these you know, work problems. All right. So Lisa. All right, and I'll make a little table as well for this. All right. We got the work, which is in lawns, right? The rate of work, which will be in lawns per hour, because the times being mentioned in this problem are in hours. And then the time will be in hours. Right? And we have these two different people doing work, right? So again, very similar table to what I had earlier. We have Lisa working on things, and we have Barb also working on things. Right? Now, it says it takes Lisa 3 hours to mow the lawn, one lawn. So one lawn takes her 3 hours, right? So just as before, the time it would take is equal to the work divided by the rate. Right? If you have W equals RT, then T would be W divided by R. So the time it takes Lisa to mow one lawn is 1/3 of an hour. Right, so this is Lisa's rate, or I'm sorry, Lisa's time. Sorry. Barb does one lawn in 2 hours. Oops, I messed that up. I put the time and the rate in the wrong place. My apologies, my apologies, my apologies, right? We're solving for rate this time. So the rate would be equal to W divided by T, right? If W equals RT, the rate is W divided by T. My apologies. Still, very similar setup to previously. Yeah, she does one, right, so back to Lisa, sorry, she does one lawn in 3 hours. So her rate is 1/3 of a lawn per hour. Right, so she does 1/3 of a lawn in an hour. Barb does one lawn in 2 hours. All right, so again, time 2 for Barb. Rate would be work divided by time. So Barb's rate is half a lawn per hour. So Lisa does a third of a lawn in an hour. Barb does a half a lawn in an hour. Now comes the equation. Now I'll draw a little picture here. All right, say this is one lawn. Maybe this will help. All right, here's one lawn to be mowed. And I'll do Lisa in this color. So 1 hour later. Let's say we go 1 hour later. Well, Lisa does a third of a lawn in an hour, so let's break this into thirds, and Lisa will have done this much of the lawn. Right, here's Lisa. I'll put a big L here for Lisa. Right. So after 1 hour, Lisa's done that much, and then half the lawn will have been done by Barb. Now, if I break the big lawn up into two pieces, here's half. Half the lawn will have been done by Barb, right? So I'll put a B in there for Barb. So you see, after an hour, they'll have done this much of the lawn, right? So after 1 hour, Lisa and Barb together have done 1/3 plus 1/2 of a lawn, of one lawn. Right, I hope that makes sense from this picture. All right, after 1 hour, right, we're saying Lisa does a third of a lawn in an hour. So Lisa did this third, and Barb did half a lawn in the hour. So together, right, if they work together, they'll have now a third plus a half. You need a common denominator. That's 2/6 plus 3/6. That's 5/6 of a lawn. So this gives me their rate of work. Right. So I'm going to make kind of a third column here. Again, work, rate, time. So this is where it differs a little bit from the distance problems. Together, right, Lisa and Barb together, they do one lawn. Right, they do one lawn. Oh, sorry. They don't do one lawn in an hour. They do their rate though. Their rate is 5/6, 1/2 plus 1/3. Right. They do this amount plus this amount. They do 5/6 of a lawn per hour. Right. They do 5/6 of a lawn per hour. And the question is, how long will it take them to complete one lawn? Right. So one lawn's completed. They work at a rate of 5/6 of a lawn per hour. Right? Again, just adding their rates up. And this is the unknown here. Right. You can call this X, or they're calling it little t. Right. So how long to mow one lawn together? Right, so the key to all this is adding up the rates. Right? If you know the rate at which one person works and the rate at which the other person works in an hour, lawns per hour, jobs per hour, the sum of those will be how many jobs they do in an hour together. Right. And then we have work equals rate times time. So 1 equals 5/6 times t. Right? Work equals rate times time. And then here's the fraction 5/6. So I would multiply both sides by 6. We have 6 equals 5 times t, and then divide by 5. T equals 6/5 hours. Right? And this is time in hours. This is the solution to my little equation. Now, again, the equation is always the hardest part to set up, and I think the trickiest part of these work problems is understanding that the sum of their individual rates is going to be their rate together, their rate of work together. Right. So 1/3 plus 1/2, 5, 6. Right? So keep that in mind. Right? The sum of their individual rates will be their rate of work together. And this will be the way it is for all these work problems. So yeah, 6/5 hours. Now notice, they're trying to trip you up. Look at this. I'll make this bigger. Right. Don't put 6/5 here. Look at the units. Minutes. All the times I was given is in hours. They're asking us for minutes. How many minutes does it take for them to do a lawn together? So hopefully you understand how to convert from hours to minutes. I would just multiply by, there are 60 minutes in 1 hour. So, hours would cancel. And, 5 goes into 60 12 times. And then you just have 6 times 12, 72 minutes. All right, so the time it would take them together to complete a lawn would be 72 minutes. And that's what I'll enter. All right, one more time though, the key to these work problems will be understanding that the sum of their individual rates is the rate of work together. All right. We finish up though with 72 minutes. All right, so a little over an hour. And hopefully it makes sense from my picture too, right? That little drawing I did. Right? Because after 1 hour, 5/6 of the lawn is done. So just a little over, it'll take just a little more time to finish it off, and it would just take another 12 minutes. Right? So I entered 72, submit. Wonderful. And again, they're not making tables, I don't think. Yeah. In fact, they just did the sum of their rates is their rate together. Ah, I see what they did. All right. So look back on the table here. You could have left this blank and said, hey, this rate is actually the rate they work together. The time they work together for, you don't know. They're trying to finish 1 lawn. That's the job. That's the work. And the rate would be W divided by T would be 1/T. And then you solve this equation. And this equation just ends up being the same as this equation here. These are the same equation. 5/6 equals 1/T would be the same as 1 equals 5/6T. So yeah, however you want to set it up though, you end up with the same solution. Right, 6/5 hours or 72 minutes. Right. So a little trickier, but still doable. Hope you understood. And we'll see some other work problems coming up here too as well. All right, next question. All right, so this one I'll try to do the way they had it set up. So another question involving rates of work. All right. So here Brian can lay a slab of concrete in 6 hours, meaning he can lay a 1/6 of a slab in an hour. 1/6. While Greg can do it in 4 hours. If Brian and Greg work together, how long will it take to lay a slab of concrete? And look, they broke it up into hours and minutes, so pay attention to how they're breaking up the answers here, how they want you to type it. All right, so again, here's the question. Now once again, I'm going to make a little table. We have work equals, the rate of work times the time, or the rate, right? Rate equals work divided by time. We're going to be using that a lot. All right, this time I'll make three rows all in one table. All right, we have Brian we have Greg. Oh, geez. Sorry. Let me pause this. I meant to put those over here. That's the work column. Alright, I'm going to rewrite it and come back. Alright, so sorry about that. I just jumped to, I rewrote the table. Again, work column, the rate of work, the time, and then just off to the side, remember the formula we're going to end up using here, that rate of work is equal to work divided by time. The work is in slabs of concrete, right? Slabs. The rate will be in slabs of concrete per hour, right? Because the time was given to us, times were given to us in hours here. And we have Brian, Greg, and then together, them working together. Alright, so reading through one more time, filling in the table. Brian can lay one slab of concrete, right, one slab, in 6 hours. So his rate of work is 1/6, right, work divided by time, of a slab per hour. Greg can lay one slab in 4 hours. And then work divided by time. The rate at which Greg works is 1/4 of a slab per hour. Now together, they want to lay one slab. You don't know how long it's going to take them, so call that T or something, right? This is unknown. So the number of hours, the amount of time it takes them to lay the slab is unknown. And then the rate at which they do this together would be 1 divided by T. And remember, the sum of their rates will be equal to the rate that they work together. Right. So here's the equation. So the rate at which Brian works plus the rate at which Greg works, 1/6 plus 1/4 of a slab per hour, should be equal to the rate at which they work together, which is this 1/10 slab per hour, 1/T. Alright, let me pull up, let me make this bigger now. Alright, we'll solve this equation for T. Alright, so rational equation, right? Equation with fractions, find the LCD. Right, now the LCD here would be 12T. I'm going to multiply everything by 12T. Both of these terms over here, this term here, and the whole reason to multiply it, again, we're going to distribute on the left. The whole reason to multiply by 12T it is to cancel all these denominators. 1/6 of 12T is 2T, plus 1/4 of 12T is 3T, and then 12T times 1/T, the T's would cancel, I'd be left with 1 times 12 or 12. So I end up with 5T on the left, 12 on the right. T equals 12/5. 12/5 hours. Alright. Now 12/5 hours. 12 divided by 5. 5 goes into 12 twice. That's 2 and 2/5 hours. If you write it as a mixed number. So that's 2 hours. And then let's take that off to the side here. Let's take that 2/5 hours and multiply it by 60 minutes per hour to get minutes, right? The hours will cancel, and that's 24. 2 hours and 24 minutes. All right, 2/5 of an hour is 24 minutes. So that's what they have. That's what they're wanting from us here. Break it up into whole numbers of hours and then minutes after that. So the time it takes them both to lay one slab of concrete would be 2 hours and 24 minutes, right? If they both worked at the same rate, if they both worked together. Right. And submit and look at the equation they set up, the same equation I did, I think, right? 1/6 plus 1/4 equals 1/T. Look at that. The sum of their rates equals their rate together. And then you're solving for T. And and they wanted you to break it up into hours and minutes. Again, please pay attention to the units in those answers. All right. So, next question. Now we're back to uniform motion, right? The distance equals speed times time, right? Distance equals rate times time. All right, so Bill wanted to try out different watercraft. He went 62 miles downstream. Downstream means, with the current. So you're going faster than you would if you were going upstream. Right? Upstream means against the current. So 62 miles downstream in a motorboat and 27 miles downstream on a jet ski. Right? So both times he's going downstream. Fine. Right? Just pay attention to that. Sometimes they might be upstream and go slower. Alright, so both times he's going downstream, once in a motorboat, once in a jet ski. His speed on the jet ski was 10 miles an hour faster, mph, miles per hour, faster than in the motorboat. Bill spent a total of 4 hours on the water. What was his speed in the motorboat? Which they're calling R here, right? So I'll use R for that. Alright, so once again I'll pull up a piece of paper here and make this table. We have distance equals rate of speed times time. And I feel like, because they talk about the total hours and all that, the time, right, time is equal to distance divided by rate. Or you could have rate equals distance divided by time, but I feel like we're going to use this one. Right. Table. Then we got the motorboat. Let's put boat. The boat row, and then jet ski. The distance traveled downstream on the boat was 62 miles. The distance is in miles. The rates of speed are in mph, miles per hour, and times are in hours. Right? I like to put the units above the columns. The time, we don't know. The jet ski went 27 miles downstream. Now these rates, see, the question at the end was, what was his speed or rate of speed, in the motorboat? So in the boat, that rate of speed, they're calling that little r. Right? So I'll call that little r. That's the unknown. I assign a variable to it. And it was mentioned that the speed on the jet ski was 10 miles per hour faster than the motorboat. So it's the motorboat's speed plus 10. And now we can write some expressions for the time by taking the distance expression divided by the rate expression. The time on the boat was 62 divided by r, hours. And the time spent on the jet ski was 27 divided by r plus 10, whatever that is, hours. Alright, so I've got all the information in. So I'm going to make this a little larger for you. And just as before, it was mentioned in the problem that the total time spent on the water was 4 hours, or equals 4 hours. So this time on the boat plus this time on the jet ski should be 4. Right. So here's our equation, 62 over r, right? That was the time spent on the boat, plus 27 over r plus 10. The time spent on the jet ski should be equal to 4. And we're solving this equation, and the value of r there represents the speed of the boat. Alright, so just like all the others, least common denominator. Now the least common denominator is pretty obvious here. It's just r times r plus 10. Right, r times the quantity r plus 10. And I'm multiplying every term by this, right? So I'm just going to write this. Right, we're multiplying both terms, both of these fractions on the left by LCD, and then the right side by the LCD as well. So the first fraction on the left, the r's would cancel. I have 62 times r plus 10 left. Plus the second fraction, the r plus 10s would cancel. I'd have just 27r. And then the right side, I'd have 4 times r plus 10. Nothing canceled. And this will end up being a nice quadratic equation, nice polynomial equation here. distributing the 62, we'd have 62R plus 27R, that'd be 89R plus 620 on the left side equals, and then distributing the 4R here, 4R squared plus 40R, and then taking everything to the right, and then I'll switch sides, so we have 4R squared subtracting 89R would give me minus 49R, and then subtracting 620 minus 620, right? So I have everything on one side and 0 on the other. Alright, then I'm gonna think about how to factor this, and I'll be right back with you. Alright, so I thought about how to factor it a bit. I did the AC method, and I got 4R plus 31 times R minus 20. And you can check by foiling, you get that back. Alright. And by the zero product property, the only way a product is equal to 0 is if one of the factors is 0. Now this first factor, 4R plus 31, would be 0 if R were negative 31/4. The other factor would be 0 if R were equal to 20. And once again, these both work. They both work. They would both make this table make sense. The only thing is, though, one of them doesn't make sense for the problem. The values work in the table, sure, but just like in the first question in this video, having a negative speed doesn't make any sense. So I'm going to cross this one out here, negative 31/4, because it doesn't make sense in the problem. The only one that does is 20. Right. So if R were 20, or if the boat had a speed of 20 miles per hour, then the jet ski would have a speed of 30 miles per hour, and all this time and all the stuff in the table would make sense. Right, so back here, the value of R is 20 miles per hour. Great. And again, please read through the answer explanations. Next question. Back to another rate of work problem. So again, the key to these problems is to remember that the sum of the individual's rates of work should be equal to their rate of work together. Right. So you're washing his dad's car alone. 8-year-old Levi takes 2.5 hours. If Dad helps him, then it takes 1 hour. How long does it take Levi's dad to wash the car by himself? And again, notice the breakdown in hours and minutes. Right. I'm going to pull this up. Here's a piece of paper. I'm going to make a table like I've made for the other work problems, right, this time with 3 rows. So we got work, rate of work, and the time. And the work will be in cars, right? How many cars can they wash? Rate will be in cars per hour, and time will be in hours. I'm going to put 3 rows here. Got Levi, Levi's dad, and then them together. And don't forget off to the side that the rate of work is equal to the work divided by the time. That'll be used here. So washing his dad's car alone. So Levi can wash 1 car, under the work column, can wash 1 car in 2.5 hours or 5/2 hours. I like fractions. That's 2.5. Now 1 divided by 2.5 is 2/5, right? 1 divided by 5/2 is the same thing as 1 times 2/5. Right? So here's Levi's rate. He can wash 0.4 cars per hour, or 2/5 of a car in an hour. Now they mentioned together next, so I'm not doing dad alone yet. if Dad helps him, it takes 1 hour. So they can do 1 car in 1 hour together. So the rate at which they work is a car an hour, 1 divided by 1. Now the question is, how long does it take the dad to wash the car by himself? So if Dad washes 1 car, in how long? We don't know. He can wash 1 car in T hours. And the rate at which Dad works then is 1 over T. And don't forget the relationships between, the sum, right? The sum of the individual rates should be equal to their rate together. So here comes the equation, the rational equation we're going to need to solve. So the rate at which Levi works, which is 2/5 of a car per hour, plus the rate at which his dad works, 1 over T cars per hour, right, with the unknown T, should be equal to the rate at which they work together, which is 1 car per hour. And then I'm solving this equation, just like any other equation with fractions. Now the LCD here is 5T, and I'm multiplying, the 2/5, the 1 over T, and the 1, right? Everything on both sides we're multiplying by the LCD. I'm multiplying by 5T. Now the first fraction on the left, we'd have 2T left over, the 5's would cancel, plus then 1 over T times 5T would be 5, the T's would cancel, and then 1 times 5T is 5T, and then subtracting 2T I get 5 equals 3T, dividing by 3, T equals 5/3 hours, which is, as a mixed number, would be 1 2/3 hours. But they want us to break it up into hours and minutes, so this is 1 hour, and 2/3 of an hour, right? 2/3 hours, you multiply by 60 minutes per hour here, cancel the hours, that's 40 minutes, right? 40 minutes is 2/3 of an hour, and that's what they want us to enter, right? Hours and minutes. So if Dad were working on his own, it would take him 1 hour and 40 minutes. And that's what we're going to enter here. 1 hour in the hours box, 40 minutes in the minutes box. Wonderful. Yeah, but the same, pretty similar setup. You just have to remember for these work problems, the sum of the individuals' rates of work will be equal to the rate of work together, if they work together. All right, please read through the answer explanations. So I got one last question here on this rates of work problem. Alright, so we have it takes Sam 4 hours to rake the front lawn, while his brother Dave can rake the lawn in 2 hours. How long will it take them to rake the lawn working together? Alright, so I'm just going to set up the equation right now. We've seen a few of these now. So Sam's rate, which is, he does rakes the lawn in 4 hours. So he can rake 1/4 of a lawn per hour. Plus Dave's rate, it says Dave can rake the lawn in 2 hours. So that means he can do half a lawn in an hour, half a lawn per hour. Should be equal to their together rate, which is 1 lawn in I don't know how many hours. So 1 lawn is raked per T hours. And I solve for T here. The LCD would be 4T, and I multiply everything by 4T, so we got T plus 2T equals 4. That's 3T equals 4, T equals 4/3 hours, which is 1 hour and 20 minutes. Alright, that's 1 1/3 hours, and 1/3 of an hour is 20 minutes. So it takes an hour. It would take 1 hour and 20 minutes for them to rake a lawn together. Right? Very, very simple stuff. Again, you can set up the table and junk. I've already done 3 of them though. Just kind of want to get this moving here. So it would take them 1 hour and 20 minutes to rake a lawn together. Wonderful. And then again, please read through the answer explanations. Okay. The last couple questions have to do with that uniform motion stuff, right? Distance equals rate times time, or rate equals distance divided by time, or time equals distance divided by rate, you know, whatever one ends up giving us the fractions. Alright, so here Jill was training for a triathlon, so she planned a day of exercising. She spent a total of 2 hours riding her bike and running. So biking and running total 2 hours. Right? So the time riding plus the time biking is 2 hours. That's where the equation is going to come from. She biked for 12 miles and ran for 6. Her rate for running was 10 miles an hour less than her biking rate. What was her rate when running? Alright, so this one I'll set up the table again. Alright, I'll just pull the paper up and I'll read it out loud. You don't need to see it all the time. So again, I got distance, rate, time. We got running. We got biking. The question is, what was her rate when running? So they're calling this R. Right? So that's she's going R. She runs R miles per hour. Right. And they said that the biking rate was, her rate running was 10 miles an hour less than her biking rate. That means the biking rate was 10 miles an hour faster. R plus 10. Whatever these expressions are, the running rate should be 10 less than the biking rate. That's why the biking rate is 10 more. Right. Hopefully that makes sense. The distance she ran for was 6 miles. The distance she biked for was 12. So the time running would be 6 divided by R, hours. And the time biking would be 12 divided by R plus 10, hours. And the total, total is 2 hours. The total time spent running and biking was 2 hours. So we have 6 over R, the time running, plus 12 over R plus 10, the time biking, should be equal to 2 hours. And I'm solving this equation. Alright, so the LCD is pretty obvious here, right? It would just be R times R plus 10. And I'm multiplying everything by that LCD. Multiplying both the fractions on the left and every single term on both sides. First, on the left, R's would cancel. You have 6 times the quantity R plus 10 left over. Plus, second, the R plus 10s would cancel, leaving me with 12R. And then on the other side, you just have 2 times the LCD, 2 times R plus 10. Alright, left side, distributing the 6, we'd have 18R, right? 6R plus 12R, 18R plus 60, 6 times 10, equals, and over here, distributing the 2R, we have 2R squared plus 20R, and then taking everything to the right side, and then I'll switch sides, we get this quadratic equation. You have 2R squared. I'm subtracting 18R to give me positive 2R over there. Just positive 2R. And subtracting 60. And something I'm noticing is that all the coefficients here are even. They're all multiples of 2. So I'm going to divide both sides by 2 right now, make the numbers a little smaller. We have R squared plus R minus 30 equals 0. And then this factors to R plus 6 times R minus 5. Right, so the possible solutions are R equals -6 or R equals positive 5. The only one that makes sense for the problem is the positive one, right? Because having a negative speed doesn't make any sense for the problem, right? Speed shouldn't be a negative quantity. So And remember, r was the running speed, right? From my table here, r did represent the running speed, which is what they were asking me for. So her running rate is 5 miles per hour. And yeah, so I got 5 there. Alright, and again, please read through your answer explanations. Alright, final question should be another distance problem, uniform motion problem. Distance equals rate times time. Okay, this one's a little different. The previous 3 questions in this objective mentioned the total time, and that's where the equation came from. Now this one still has time mentioned, right? So once again I'm going to do a table, and this time I'll actually I'll read through it first. We have Matthew jogged to his friend's house, 12 miles away, and then got a ride back home, so the same 12 miles. It took him 2 hours longer to jog from his house to his friend's house than it took for the ride back. His jogging rate was 25 miles per hour slower than the rate when he was riding home. Right? What was his jogging rate? And again, they're calling this R. Right? So once again, I'll pull up a table. I'll let you read the problem this time again. Right? So we have distance, we have rate, speed, we have time. And we have a jog, from Matthew's house to his friend's house, and we have the car ride back. Now both of them are 12 miles. I hope you understand that, right? Jog to the friend's house, that was 12 miles, rode back, it's the same 12 miles. Right? The rate at which he's jogging, right, that was what's being asked for. Call that R, the rate of jogging, R miles per hour. And they said that this was 25 miles per hour slower than the car. Right? So the car is 25 miles an hour faster. Right? So for the ride, it's R plus 25. Now the time jogging would be 12 divided by R. The time riding would be 12 divided by R plus 25. Now here's where you gotta be a little careful. That sentence, it took him 2 hours longer to jog there than to ride back. So the time jogging was 2 hours more than the time riding in the car. This is the sentence, was, is, that's where the equals is going. All right, so let me pull up make this a little bigger. All right, so the time jogging was 2 hours longer than the time riding. The time jogging was 12 over R. Was, is, right, equals 2 hours more than the time riding. The time riding was 12 over R plus 25. And then 2 hours more than that, right, plus 2. So hopefully this makes sense, right? So if it took them 3 hours to ride, it would have taken 5 to jog, right? 3 plus 2, right? Whatever the time it took to ride back home, add 2 to that, and that's how long it took them to jog there. Right, so you see it's a little different than the previous examples with totals and stuff. All right, but no different than any other one, though. We're solving an equation with fractions. The LCD is, R times R plus 25 here. Again, pretty obvious. I am multiplying, the single fraction on the left and both these terms on the right. There's 2 terms on the right. Multiplying everything by this LCD. And the reason for doing that is to cancel fractions. That fraction on the left side, the r's would cancel. I'd have 12 times the quantity, R plus 25. Then equals, and then the first term on the right, the R plus 25s would cancel. I'd have 12R plus, and then 2 times the LCD. Nothing's canceling there. 2 times R plus 25. And this is going to end up being another quadratic equation. So left side, you know, there's going to be 12r plus 300. All right, 12 times 25. Yeah, that'd be 300. Right, 4 goes into 12 3 times. Yeah. Equals, and here I'm distributing the 2r. We have 2r squared plus 50r, but then another 12r, so plus 62r. And then I'm going to take everything to the right side again, and then I'll switch sides. So we'd have 2r squared, subtracting 12r gives me plus 50r, and subtracting the 300 gives me minus 300. And then just like in the last example, noticing all these coefficients here are even, so I think just to make the numbers a little smaller, I'm going to divide both sides by 2. So now I have r squared plus 25r minus 150 equals 0. And let's see. Yeah, so I'll try factoring this and be right back. Okay, so seeing this now here, we got r, and I'd have to have plus 30 and minus 5. Right? Does that make 30r and minus 5r for the 25r and then minus 150? Alright, so the possible solutions are negative 30 and positive 5. And once again, they both work in the equation, but they don't both make sense for the problem, right? Having a speed, remember r represented jogging speed, right? The rate of speed for jogging. So having a negative speed doesn't make sense. So I get rid of the negative solution. The only one that makes actual sense here is the 5 miles an hour, right? So this person, Matthew, was jogging 5 miles an hour and would have been riding 30 miles an hour, right? 25 more, but they asked for the jogging speed. Right? R equals 5 miles per hour. All right, so you see that all the, the uniform motion problems were similar. I set up a similar table, and we ended up doing time was distance divided by rate. And all those work problems, we ended up using the same concept that the sum of the individuals' work rates was equal to their work rate together, right? And then an equation usually came from that. And then you solved all the rational equations the same way. You found the LCD, multiplied both sides by the LCD, and solved the resulting equation. And then again, you only looked for the solutions that actually made sense, right, in the context of the question. All right, so a lot of stuff there, but that's it for this version of this assignment, section 7.5 part 2. Once again, I'll say that the questions I saw here may or may not be exactly the same as the questions that you see when you work on the assignment, but the objectives are the same. The types of questions are the same. How you would go about doing them would be similar. So I'm hoping that watching me go over these 8 examples here help you when you're working on similar problems, working on the assignment on your own. And thank you for watching.